Hello, welcome to CSC7013, Advanced Math for Computer Scientists. This is Brady Chen. This is Module 6, Set Theory. Set theory is the mathematical theory of well-determined collections called sets of objects that are called members or elements. Now here's the learning objectives for Module 6. Now first we will introduce the concept of sets, and then we'll talk about the relationships between sets, the relations between sets. And we will talk about some of the operations on sets. So in general, a set is a conglomerate of objects. So we can define a set in two different ways. One is to describe the contents using like English language. Or we can define the set by listing the elements of the set. Now typically enclosed in curly brackets. Okay. So now here we have two examples of the sets defined by describing the contents. Okay. The first one is we can define a set like this using the English language. Say the set of all prime numbers. We know what the prime number is, right? So a prime number is a number that can be divided by either 1 or itself. Another example, the set of all books written about US history. So you can define these two sets using the first approach by describing the contents. Okay. Now also you can define the set by listing the elements. Okay. Now here are two examples. Now these two examples, we actually define sets with finite number. Okay. So the first one is we can define a set of 4 integers. So enclosed in curly brackets. Okay. This is another set. It's a set of 1, 2, 3, 4, 5 cities: New York, Boston, Austin, London, Tokyo. So now let's discuss the relations between sets. Now suppose I have two sets, A and B. Okay. Now let A be a set of students. Okay. So this way we define the set A by describing the contents, right? So it's a set of students. Okay. Now we can define another set, B. B is a set of female students. So in that case, B is also a set which is defined by describing the contents, which are the female students. Now, what is the relationship between these two sets? What's the relation between these two sets, A and B? Okay. Now, we can see that every female student is also a student. But the other way around is not true, right? Not every student is a female student. So because student could be male students or female student, or could be, something else. So in that case, we can define the relation as a subset. So we can say B is a subset of A. So that means if you use the diagram, we can use two circles to describe two sets. A, we can define A as the big circle, okay, which may contain a whole bunch of elements. These elements are students. And B, a set of or female students. So it's a subset. Okay. So we can use the notation like a B is enclosed in A. Okay, B is a subset of A. Okay, so now if John is a student, we can say that John is an element of A because A is a set of all students. So John is a student, so John is an element of A. So we use the notation John belongs to A. We use that notation. Okay. Now, if Barbara is a student, then Barbara also belongs to A. So, however, Barbara is also a female student, so therefore Barbara also belongs to B. So that's basically defines the relationship as a subsets. So in the previous slide, we talked about relation between two sets. That's the subset. So for two sets, if one set is completely included in another set, that relation is called a subset. Okay. Now, there is actually some kind of relationship between two sets that none of the set is included in the other set. Okay, so however, there's overlapping. Now let's take a look at the example. So again, let A be a set of students. Okay, A is a set of students. And now let's define another set, B. B is a set of workaholics. Okay, there's another set B. Now what's the relation between A and B? Now, if some of the students are workaholics, but not all the students are workaholics, okay? So there might be overlapping between A, the student, a set of students, and B, a set of workaholics. Now, among workaholics, there are students, but not every workaholic is a student. So that means, so there is some overlapping here. So for each element in the overlapped area belongs to both A and B. So that means each element belongs to both student and workaholic. Now the area over here basically contains all the students that are not workaholic, but every element here represent the workaholics that are not a student, right? So this relationship defines the overlapping. So far we have talked about two relations between sets. One is called a subset, the other one is called overlapping. The subset basically means one set is completely included in another set. Now, the overlapping basically means none of the sets is completely included in the other set. However, they have some common area. Okay. Now, here we're going to talk about another relation between sets, and this is called disjoint sets. Now, let's take a look at an example. So suppose A is a set of people who support the Red Sox. Okay, so these are the group of people who support the Red Sox. And B is a set of people who don't support Red Sox. Okay. Now, what do you think? What's the relation between these two sets? Is there any overlapping between A and B? Which means, can we find anyone who supports Red Sox and in the meantime doesn't support Red Sox? The answer is no, right? You cannot. So in that case, these two sets do not have common elements. Okay, so this relationship is called disjoint sets. Now here's another relation between two sets. Okay, so let's take a look at these example. Now suppose A is a set of numbers divisible by 6. Okay, now B is a set of numbers divisible by both 3 and 2. So now let's take a look at these two sets. Okay, so A is a set of numbers divisible by 6. That means now we can easily find some members of the set, right? So let's say for A, 6 is definitely belongs to A, right? And 12 is an element of A, right? Because 12 is divisible by 6. So basically, A contains all the elements which are multiple of 6. Okay. Now let's look at the B. Now B is divisible by 3. So then we can say, okay, let's find some elements for B. Let's take a look at 3. So 3 is divisible by 3, but B also divisible, element in B also divisible by 2, so 3 cannot be divided by 2, right? So 3 is not B. So we end up, it end up that we find out now all the elements can be in B can be divided by both 3 and 2. So in the end, all the elements in B should be divisible by 2 and 6, which is 2 times 6, which is 6. So B is actually pretty much the same, contains the same elements as A. So in this case, technically A and B are basically the same, right? So that relationship is called equivalent sets. Okay, so if we draw the diagram, we're going to say, okay, this is A. Now where's B? And this is B. So they're completely overlapped. Okay, so obviously every element of A is an element of B, and every element of B is also an element of A. So that's equivalent. So let's look at an example. So suppose A is a set of New England Patriots fan, B is New York Jets fan, and the C is a Boston Red Sox fan, and the X is a set of sports fan, right? So let's find the relations between these sets. Can we draw the circles to illustrate the relationship? You notice, we can just have a circle with an overlapping with, the subset, something like this. So, but before we draw it, let's discuss some of the interesting questions. So, if A is a set of New England Patriots fans, so if I'm a New England Patriots fan, do you think I could be the New York Jets fan? Now, if you know a little bit about the history between Patriots and the Jets, you know that that's not really possible, right? Even though technically Patriots and Jets are different, sports, sports team. So teams, they some people could be the fan of both, but that's really not possible. So I'm gonna say, if I draw this, if A is a Patriots fan and B is a Jets fan, so A and B has nothing in common. Okay. Now C is a set of Boston Red Sox fans. The Red Sox is another sport, right? So do you think it's possible that the Red Sox fan could also be a Patriots fan? The answer is yes, right? But do you think the Red Sox fan could be a Jets fan? Well, it's still possible, right? So you can put something like this, okay? That's C. It's still possible. Let me actually put the A here, okay? Let me actually delete okay, clean up the A. Yeah. So some of the Jets fan could be a Red Sox fan, but Jets fan cannot be a Patriots fan. Now what about X? X is a set of sports fan. So that's the total, right? Because the sports fan could be any sports fan. So the Patriots fan is a sports fan, Jets fan is a sports fan, and Boston Red Sox fan is a sports fan. So X could be the total. Okay. So what's the relationship? The relationship between A and B are disjoint. Okay. Relationship between A and C is, what is that? Overlapping, right? And relationship between A and X is subset. Okay. Now here's another example. So A is a set of people who speak English, B is a set of people who speak French, and C is a set of people who speak Spanish. And X is a set of people. That's all the people, right? Can you draw the circles to illustrate the relationship? Okay. I'll leave that question for you. Okay. So here's the checklist for the previous example. So remember, we have 3 sets, or actually 4 sets, right? A is set of people who speak English. B is a set of people who speak French. And C is the set of people who speak Spanish. And X is a set of people. Okay. So now the first one we need to check is, do we have this? So make sure in your drawing A, B, and C are subsets of X. Okay, does your drawing represent this? Okay, now in your drawing, do you include the people who speak only English, or only French, or only Spanish? Or do you include the people who can speak only 2 languages, not the other one? For example, like English and French, but not Spanish. English and Spanish, but not, I think it's French. And French and Spanish, but not English. Right? Do we include this case? And also, do we include the group of people who can speak all the language, English, French, and Spanish? So you need to check these. Okay. Now let's talk about a set and its elements. Okay. We use the notation. We use the notation to represent the element of a set. So suppose we have a set A, then if X is element of A, then we say X belongs to A. So therefore, if A and B are two sets, okay, then if two sets has a relationship, A is a subset of B, then A is a subset of B, then we normally use this. Okay, that means that for every element of A, it's the case that that element also belongs to B. Okay, so that means all elements of A are also in B, but not necessarily the other case. For example, let's A to be a set of some numbers 1, 2, 9, 7, minus 2. Okay, it contains 5 elements, and B is 1, 3, 2, 3, 9, 4, 7, minus B. Then we take a look at the elements of A and B. We find out every element A in A, like 1, 2, 9, 1, 2, 9, these are also elements of B, and 7, 2, 7, 2. So in that case, A is a subset of B, right? So that means if A belongs to A, X belongs to A, then it's true that X belongs to B. But not the other case, because we can find an element in B which is not in A. Okay. And also that if we talk about the other cases, that sometimes if A and B are overlapping, let's say A equals 1, 2, 3, and B is 2, 3, 4, then we can find out that A and B intersect if there's an X such that the X belongs to A and X belongs to B. And now we can find out two elements, right? That one is definitely an element of A, but one is also an element of B. Oh, I'm sorry, I take it back. 2. 2 is an element of A, and 2 is also an element of B. Also 3, right? 3 is an element of A, and 3 is an element of B. So you have two common elements. So that basically tells us that the A and the B are overlapping. Okay. The last case that when we try to say A and the B are equivalent, then if A is 1, 2, B is 1, 2, then A and B are equivalent, right? Now, in many cases, we want to discuss the relations among the sets. Okay, for example, we can define a set of all students. Okay, and we can define another set, like a set of teachers. Okay, and a set of C, let's say, software engineers. Okay, we can discuss a various different group of people. Okay. Now, so these sets may have some kind of relationship. Maybe one set is a subset of the other, or so they may have overlapping, then or they're disjoint, right? However, none of the sets basically, consists of all the object we are interested in or we are considering. Okay. Now, what is this? So sometimes it's always easier to think about the biggest set we're considering in our problem. Okay, we can call this set a universal set. It could be the set of all objects under consideration. Now, what could be the set we can define for these set A, B, and C? So we can define a set like called a universal set as set of people, right? So in that case, A is a set of students, which is a subset of U, set of people. B is also a subset of U. C is also a subset of U. And these U basically consists all the elements we are interested in or we are considering. Now we call this a universal set. Okay. So another example is like if we define A is a set of children, B is a set of senior citizens. So A and B are disjoint, right? You cannot, have an element which belongs to both A and B, right? If a person is a child, then that person cannot be a senior citizen, right? And vice versa. So, but these A and B do not exhaust the U, as there are adults who are neither children nor citizens. Okay, so that's why in any problems we can define a universal set, which basically contains all the objects under consideration. Okay. Now, with the definition of a universal set, we can define another operation called complements. So let's take a look at that case. A is a set of people who are US citizens. Okay. B is a set of people who are not US citizens. Okay. So definitely A and B are disjoint, right? But A and B basically exhaust the whole universal set, right? So that means A and B are basically a subset. You can define the universal set as the set of people. So in that case, A, all the people plus in A plus all the people in U basically makes the whole universal set. And in this case, we call A is a complement of B. So we can write this. A equals the B to the C. C basically means complement. And in this case, B is also a complement of A because they basically exclude each other. But they combine these two group of people, you're going to make the whole universal set. So now here's the definition of a complement. Now suppose we have two sets, A and B. Now A is a complement of B if it includes all elements of U that are not in B. So the key is actually the set U. U should be the set of all objects under consideration. Let's take a look at the example. Now suppose U is the set of all whole numbers. Okay. Now if B is a set of all even numbers. Now what's the complement of B? Let's say A is the complement of a B. So A should contain all the elements in U, right? All the elements of U that is not in B. So A should contain the numbers that are not even number. So what is A? The set of all odd number, right? Because the set of whole numbers basically contains like a 0, 1, 2, all the actually natural number, and a -1, -2, and -3, Now B is a set of all even numbers, so that means B contains these numbers. If we think a 0 is also an even number, then A is going to be all the odd numbers. Okay. Okay. Now suppose B is all the positive numbers, right? So what is the complement of B? So the complement of B, which is A, should be all the negative numbers, right? Is that right? This is not complete, right? Because if you look at this U, B is all the positive numbers. So B should be the numbers starting from 1 and 2 and 3, all the positive numbers. Now, the complement of B should be all the numbers not in B, right? So that should include all the negative number plus 1. Oh, I think plus 0. Right. So you make sure that you include every element in U, but not in B. So don't forget the number 0. So we introduced the concept of sets and discussed the relations between sets. So now here we're going to talk about certain of the operations on sets. Okay, so basically there are 3 operations. Okay, these are 3 basic operations. One is called a union, and then intersection, and a complement. Okay, so for example, if we assume A is a set of birds and B is a set of cats, so A and B are different sets. Now, based on the discussions in the previous slide, we know that A and B have nothing in common, right? So these are disjoint sets. However, can we actually do any kind of operation, perform any kind of operations, for A and for B? So we can actually create a new set based on these 2 sets. So that's something we're going to talk about. So let's look at the first operation, the union. Now we use the notation A union B. Okay. Suppose A is a set and B is a set. Then A union B, we use the notation. Looks like a English letter U. Okay. Now to define union, let's consider two definitions of the same operations. Okay. So you can define the union in two different ways. Okay. Now definition one, it's based on the elements of these sets. So to make a union of A and B, take all the elements of A and all elements of B. You take all elements of A and all elements of B and put them together, and the resulting set would be A union B. Okay, so this definition is based on the elements of the sets. Now the second one, we can define the union like this. Okay, suppose if you have element X, if element belongs to the A union B, if and only if A belongs to A or X belongs to B. Okay. So that defines the union of A and B. Now let's take a look at the example. Just use the example of previous slide. If A is the set of birds and B is the set of cats. Okay. Now what's A union B? So based on the definition 1, basically A union B and the set is the set of birds or cats, right? So that's the definition of union. That's the example that how we can actually combine two sets together and create the union of these two sets. Okay. Now let's take a look at some more examples. Okay. Now first example, suppose A is a finite set which contains some numbers 1, 2, 3, 4. Okay. Now B contains 3, 4, 5, 6. Okay. So let's see, what is A union B? So you basically use the definition 1. You can put all the elements in A and all the elements in B together. There's actually redundant, right? So we just need to take one copy. So you have a 1, 2, 3, 4, and then B has a 3 and a 4, so it's already included. So we just put a 5 and a 6. Okay, so that's A union B. Remember, for every set, you cannot have a redundant element. Okay, so one of the element has to be appear once in a set. Let's take a look at another example. Okay, suppose I have a set. I can use different notation instead of A and B. I can say X equals the set of all numbers divisible by 3. And y is the set of all numbers divisible by 2. Okay, now what is a x union y? It's a set of all numbers, because remember the definition, you just combine all the possible elements from A and all the possible elements from B and together. So the set of numbers divisible by 2 or 3, right? So if it's divisible by 3, that means that element belongs to x. So this element should be in the union of x and y. Now if the number is divisible by 2, so that element belongs to y. But that number should also belongs to x union y, right? So that x union y should include both the element, okay, the element both either belong to x or y. So that's another example of the union x and y. Okay. Now let's take a look at the other example. Let's say, okay, I'm going to use A, the set of all even numbers. B, the set of all odd numbers. Now what is A union B? So the A union B is going to be the set of all even numbers or odd numbers. Okay, what does that mean? So it's a set of all whole number, right? Okay, whole numbers. Let's see, any other example? Okay, let's take a look at the last one. We can use I is the set of all negative numbers. And J is the set of all positive numbers. What is I union J? Yes, the I union J is a set of all positive or negative numbers. Okay. You cannot say it's the set of all whole numbers, because if you want to claim the set contains all whole number, you have to include 0. But I union J does not. This is a new set, but it does not contain 0. Okay. Or you can say I union J is the set of all non-zero whole numbers. That should be okay, right? It does not include 0. Now here's another operation. It's called intersection. Now for intersection, we use the notation A intersection B. It looks like the English letter U, but it's upside down. Okay. Now to define an intersection, let us consider two definitions. Again, we have two definitions. Definition 1 and definition 2, which is which are very similar to the definitions for the union. Okay. Now first, to make an intersection of A and a B, suppose we have two sets, A and a B. And to make an intersection of A and a B, take only those elements of A and a B that belongs to both sets. The resulting set will be A intersection B. Or we can use another definition. Definition 2 says, if an element X belongs to A intersection B, if and only if X belongs to A and X belongs to B. Remember the and, because for union it only say X belongs to A or X belongs to B. But now for intersection we have to make sure X belongs to A and X belongs to B. Okay. Now you can clearly see the difference between the union and intersection, right? So now take a look at the example. Okay, again, let's say A is a set of people who speak English. Who speak English. Okay, English. And a B equals a set of people who speak Spanish. Okay, now what is A union B? So that's the set of people who speak both English and Spanish, right? So therefore, if you know that the X is in the intersection of A and B, then X must be in A and B. Now, let's go back to another example. A is the set of birds, right? And B is a set of cats. Now, what is A intersection B? It's a set of animals, so that means it belongs to both A and B. So that means that animal must be both birds, both a bird and a cat. That's not possible, right? So there's no overlapping between A and B. So A intersection B must be an empty set. So there's nothing in there. Sometimes we use phi to represent an empty set. Okay. Now let's take a look at more examples of intersection. So we're going to use the similar examples that we used for the union. So let's say A is a finite set 1, 2, 3, 4, 5, and the B is another finite 8, 3, 4, 5, 6, 7. Now what is A intersection B? So we remember by definition, for every element in the intersection of B, that element must be in both A and B, right? So let's take a look at each of the elements in A. So we look at the number 1. 1 is in A, however 1 is not in B, right? So 1 should be excluded. 2 should be excluded because it's not in B. Now 3 also appears in B. 4, yeah, 4 is in A, but also in B. And 5, yeah, in both A and B. Now the other element 6 is in B, but not in A, right? 7 is in B, not in A. So these should be excluded, right? So A intersection B should be 3, 4, and 5. Okay. Now let's take a look at another example. X. Let's say X is the set of all numbers divisible by 3. And Y is the set of all numbers divisible by 2. Remember A union X union Y, right? X union Y is the set of all numbers divisible by either 3 or 2. Okay. Now what is the intersection? What's the intersection of X and Y? Again, if X belongs to X and Y, that means X must be divisible by 3. But in the meantime, X must be divisible by 2, right? So what is the intersection of X and Y? So it's a set of all numbers divisible by both 3 and 2. Now, what kind of number that are divisible by both 3 and 2? So you can, for simplification, I think that's good enough. Okay. That should be, well defined the X intersection Y. But you can simplify these. You can say, okay, if divisible by both x3 and 2, then it's a set of all numbers divisible by, you can multiply 3 and 2 by 6. Now these are the same set. So it's actually a simplified version, but anyway, it doesn't make any difference. You can also just express the X intersection Y with that statement, but you can use that one as well. So that's the examples of intersection. Let's take a look at another one. Say I is the set of numbers. Okay, I'm going to say set of all even numbers. And J is the set of all odd numbers. Okay. Now remember I union J, right? So it's the set of all even or odd numbers. But what is I intersection J? Intersection J. Can we find a number that is even number, but also in the meantime it's a odd number? The answer is no, right? So that means what does that mean? So the intersections of I and J should be empty set. Okay. Now complement is another operation. So we use the notation A to the C to represent the complement of A. Okay, so A to the C is a notation for complement of A. Now also we can define the complement in two different ways. So definition 1, to take a complement of A, take only those elements of universal set that are not in A. Then the resulting set will be the complement of A to the C. So in that case, in order to define a complement, we need to agree on a universal set. Okay. What is universal set? It's a set of objects under consideration. So when we actually talk about a complement, you have to, we have to agree on what's the set that include every element we're considering. Okay. Now the other definition is, so if an element X belongs to the complement of A, so suppose a complement A is another set, then if and only if A does not belong to A. So if A does not belong to A, then A belongs to the complement of A, or vice versa. That's the second definition. Now, with the concept of complement, then the question is, what would be the complement of a universal set? So the universal set supposed to basically contains all the elements we're considering. Now the complement of the universal set, that means the element in the complement of universal set basically belongs to something that other than the universal set. So that means basically it does not exist, right? Because the universal set already contains everything we are interested in, but the complement of a universal set basically contains nothing. So that's, we use the empty set. So basically the universal set and the complement of the universal set u to the c is actually the empty set. So let's take a look at the example again. So we think about the set of numbers let's say divisible by 3. Okay. Now, what's the complement of C? So the first thing we need to figure out is, in order to define the complement of X, we need to figure out what's the universal set. Now, logically, we can assume the universal set is the set of all numbers, or whole numbers. And then, so the complement of C basically is a set of all of numbers not divisible by 3. Okay. Every numbers. As far as they're not divisible by 3, then that's the complement of C. Okay. Now again, if X is the set of numbers divisible by 2. Now what is X complement? A complement of X. So it's the set of numbers not divisible by 2, right? That's definitely correct. But also we can say it's a set of numbers not divisible by 2, or it's a set of odd numbers. Now, the set of numbers divisible by 2 can be viewed as a set of even number, right? Even numbers. Okay. So that's the other example. Let's see what else we can talk about. Yeah, okay. Let's think about another example. Let's say A is 1, 2, 3, 4, 5. B is 3, 4, 5, 6, 7. Now, in order to talk about the complement of A or complement of B, now we need to define the universal set, right? So of course we can say, okay, let's define the universal set as all numbers, all whole numbers. Then the complement of A should be all the numbers except 1, 2, 3, and 4 and 5, right? That's fine, no problem. And the complement of B is basically the set which contains all the numbers except 3, 4, 5, 6, and 7, right? Now, if we define the complement as this, the universal set for A and B as 1, 2, 3, 4, 5, 6, 7. Okay. So suppose the universal set is actually the union of A and B. So that include the elements belongs to both A and B. Oh, belong to A and B. Okay. Then what's the complement of A? Now, if the universal set is also finite set, the complement of A should be the set which contains the element of U, but not in the element of A, right? So what is A complement? The complement of A. So 1, 2, 3, 4, 5 should not be in the complement of A, but 6 and 7, right? Okay, so that's the other example. So before we talk about a complement, it's important to define the universal set. Okay. Okay, so let's summarize all the notations and all the definitions we have covered so far. Okay, so we have talked about the sets, right? And also we talk about 3 operations: A union B, A intersection B, and the complement of A. And also, as a special set, we call it the empty set. The empty set is a set that contains nothing. So no element actually is contained in the empty set. The universal set is the set that contains all the elements we are considering. Okay, so that's why empty set and the universal set are pretty much the opposite, right? So that's why always remember the complement of empty set is a universal set, and the complement of universal set is the empty set. That is just the opposite. And we also can talk about a subset, right? We use A included in B. That's a subset. We use the notation belongs to, so if X is an element of A, we just say X belongs to A. And X does not belong to A. Okay, these are all the notations we're going to use. Just keep that in mind. Now, based on the definitions of the union, the intersection, and the complement, then we have some useful consequences of these definitions. Okay, so since, remember, if we say if X belongs to the union of A and B, if and only if we use IFF, X belongs to A or X belongs to B. Either X belongs to A or X belongs to B. So what does that mean? That means that if X does not belong to the union of A, if X does not belong to the union of A, that means X does not belong to A, and X does not belong to B. Right? It's pretty straightforward, because if X belongs to A, that means X must be in the union of A and B. Or if X belongs to B, then X must be in the union of A and B, right? Based on the definition. Okay, so if X belongs to A, then if and only if X belongs to the union of A and B. So that means if X does not belong to A and A union B, then X cannot be in A and B. So that's one of the consequences. The other one, if X belongs to union A, no, I'm sorry, X belongs to the intersection of A and X and Y, then X must be in X and X must be in Y. That's pretty straightforward, right? Because that's the best definition. Okay. Now, if X is in the complement of SC, then X does not belong to. Okay. Oh, let me see. There's some typo here. Okay. Let's see. Okay. It should be X belongs to A, then X does not belong to the complement of A. Okay. Or vice versa. X does not belong to A, then X cannot. If X does not belong to A, then X must be in the complement of A. So I think that's a typo. That should be A. Okay. Okay, let's take a look at some more examples. I think I can answer some of the questions, but you can actually, figure out the rest. Okay. Suppose A is a set of all positive even whole numbers. Okay. Or A is all the positive even numbers. B equals all the positive odd numbers. And U all the whole numbers. So that means that's the universal set, right? Now please answer whether each of the following statement is true or not. Okay. So 246 belongs to A. Is that true or not? Let's take a look at the definition of A. So A is all the positive even whole numbers. Okay. So is 246 a positive even whole number? Yes, it is positive. It's an even number, right? So the answer is true. Or A 0 is 0 belongs to A. So again, A is all the positive even whole number. Now is 0 positive or even number? A looks like a 0 is an even number, but it's not a positive, right? So 0 is definitely not in A. Now what about this? Minus 39. Is minus 39 belongs to B? Let's take a look at B. Or B is all the positive odd number. All the positive odd number. Minus 39, it is an odd number, right? But it's not a positive, right? So that's false. Okay. Now, let's take a look at this. 34,545. Looks like that's a whole number. Is the number belongs to A union B. Now, what is A union B? We need to figure out. A is all the positive even whole numbers, B is all the positive odd numbers. So that means all the positive even or odd numbers. That's odd numbers. So as far as that number is positive, it doesn't matter whether it's even or odd. It should be in A union B. So the answer is true, right? Now, this one, 55, is 55 belongs to A intersection B. Now, first we need to figure out what is the intersection of A and B. A is all the positive even whole numbers. B is all the positive odd numbers. Can you find a number that is both even number and a positive number? The answer is no, right? So A intersection B is an empty set. So of course 55 does not belong to an empty set. False. Okay, let's finish all. Okay, so A union B, all the positive even or odd numbers, but 234, that's a positive even whole number, right? But by definition, A union B should be all the positive even number or odd numbers. So 234 is actually in A union B, right? So that's definitely a false statement. It says 234 is not in A union B. That's not true, right? And what about this? Minus 111 does not belong to A union B. True, right? Because every number does not belong to A union B, because A union B is an empty set. Okay. Oh, I'm sorry. A intersection B is an empty set. Okay. So what is A union B? So we already answered the question. What is A intersection B? We already answered the question. So that's B is an empty set. A union B is actually a positive even or odd numbers. Okay. So what about this? Is the following statement true? A union B to the C. So that's a complement of A union B. Okay. Now remember, universal set is all the whole numbers. So A union B says it's all the positive or odd or even numbers. Okay. Now what's the complement of A union B? So that means it should be all the whole numbers that are not even number, positive even number, not a negative, oh, I'm sorry, not a positive even number, not a positive odd number. So it should be all the negative whole number. Is that true? Actually, this is not true. Why? A union, the complement of A union B include all the negative whole number. That's true, but also should include 0, right? Okay. So if you think about the whole numbers, the universal, so basically you include 0, 1, 2, 3, all the way, and minus 1, minus 2, minus 3, da da da. So A union B actually is actually all the positive whole numbers. So the complement should be all the negative whole number plus the 0. Remember that. So if we cut it half, so that's A union B, and that's A union B to the C, the complement. Now here, let's talk about another operation. Now that operation is going to combine two sets into a new set. Okay, the new set is defined as the pair of the ordered pairs of the original two sets. Okay, let's take a look at this. So suppose we have two sets, A and B. Okay, now we're going to define a new set. Okay, now we know that you can actually create the A union B, A intersection B, and for A, you can define the complement of A. For B, you can define the complement of B if we agree on the universal set, right? But here, we define another set using something called Cartesian product. So that means we're going to create a new set which consists of all the ordered pair A and B. Okay. Now, well, A belongs to A, and B belongs to set B. So it's all the ordered pair. Okay. So now we call this A times B, and that's the Cartesian product. So the Cartesian product basically means it's a new set which consists of ordered pairs, and the first element in the ordered pair belongs to A, the second element in the ordered pair belongs to B, and that's the element which belongs to the A times B. So here is an example. So let's say A is a finite set. A equals X and Y. So these A contains two elements. And B is also a finite element. B contains three elements. Okay. Now what is A times B? A times B should actually include all the ordered pairs of AB. So that means that should include, let's take a look at the first element in A. So that should be X3. So that means it's an ordered pair. The first one belongs to A, and the second one belongs to B, right? And then also X, you don't change the value X in the first, set, but you change the value of second set. So X6 and also X9. So these are three elements which basically belongs to A times B. But we're not done yet, right? So we should also include, the other pairs. Now, in the other pairs, the first element is Y. The second element is actually picked from B. So I can just say Y3, Y6, and Y9. So we should actually include all the combinations of the pairs, ordered pairs. Okay. So let's see if A is 1, 2, 3, B is 2, 3, 4. Okay. Now, So A is a set of 3 elements, 1, 2, 3. B is a set of 3 elements, 2, 3, 4. What is A times B? It should be an ordered pair, which is which contains the combination for all the elements in A and all the elements in B. So the best way to do this is to, just say define the element using the curly brace. So the first element, we can actually put the first element in A first, okay, and then the first element in B, which is 2. And then we still keep the first element in A, but we change, and we continue to do that. Now, so here's the first element, 1, which pairs with all the elements in B, which we have 3 cases, right? And then we can change the first element to 2 and pair with all 3 elements in B. So 2, 2, 2, 3. So for 2 sets, A and B, we define the Cartesian product of these 2 sets. Okay, so the Cartesian product of these 2 sets is a new set which consists of all ordered pairs. Now, let's take a look at the example. Suppose I have 2 sets, A, which contains 3 elements, and another set B, which contains 2 elements, 3 and 4. So we define the Cartesian product of A and B, which contains all the ordered pair A and B. Now, well, A is in A, B is in B. So we know that the A contains 3 elements, B contains 2 elements. So now the Cartesian product A times B contains all the combinations of the ordered pair. So now we can illustrate using the space. So suppose A is in a one-dimensional space. We call it X. So A is actually in one-dimensional space. So it contains 3 points, 1, 2, 3. And B is in another one-dimensional space. I use a vertical line to represent another one-dimensional space, Y. So many times we call this X-axis and the Y-axis, and this is the original point. So B actually is in Y, so B contains 3 and a 4. So then we have a 1 and a 2, but 1, 2 is not actually in B. Now, for the Cartesian product of A and B, it contains all the ordered pair. The first one is from A, the second one is from B. So then for each element in A, we can pair with an element in B. So that's 1 pair with 3, and then that's 2 pair with 3, right? And a 3 pair with 3, right? And then I can pair 1 with 4, and 2 pair with 4, and 3 pair with 4. Okay. So for Cartesian product A and B of A and B, there are 6 elements. A contains 3, B contains 2. So A times B, the Cartesian product of A and B, contains 2 times 3, which is 6. It's actually all the combinations of elements from A and the elements from B. So now we can define some kind of relations between the element in A and the element in B. Okay, so because once we set up a relationship for each value of A, each value A in set A, and then we can, if we can find the corresponding value in B, then we can find some kind of relationships between the set A and the set B, and that relationship is used to, to define some kind of charts or graphs. For example, the calendar years may be paired with GDP. So the calendar year could be represent the first set A, and the GPA could be, corresponding to the other set B. So for each calendar year, you can find a corresponding GDP. I'm sorry. Also, you can actually, pair the days with the average temperature. So I can say July 1st. So then you can find the corresponding temperature, which is, 68. July 2nd, 68, 69. July 3rd, 68. July 4th, 71. So for each day, I can pair with the temperature. So that way we can actually, define the relations, okay, between two sets, A and B. So now from math, that relationship can be viewed as something called function. Okay. Now function f can be regarded as relation between each object x in its first set, let's say set A, and we call this first set domain. So that's the term used in math. And the value we call f of x in the second set B, we call this second set a range. So basically we define the relations between domain and the range, and then we call that relationship a function. Now here's how the function is defined. A function f is a relation within a special with a special property. So function, you cannot just randomly define any relation, but there's a property that this property says each x in the first set is related by f to one and only one value y in the second set. Okay, so that means if you have two ordered pairs, x and y and x and z, so then y and z has to be the same element, because for each x you're going to relate to one and only one y. Now what does that mean? So let's say we have these Cartesian product, right? And then now let's find a function, f from domain A to range B. Okay. So let's do this. I change the color for this, the ink color. Okay. So let's say for each value x, okay, in the domain, which is A, okay, for each value x. Okay, so let's say first I choose x equals 1. For the value 1, then f can be defined as a function that the map, is related to one and only one y in the range. So one can be either mapped to 3 or 4, but not both. Now let's say the function I'm going to define maps 1 to 3. Okay, so that's the one for value 1 in A. Now for value 2 in A, if x equals 2, so I also going to define a unique value in B. So in this case, I pick this value. So then I'm going to say 2 going to map to 4. And again, for 3, I need to pick a 1. So I'm going to map 3 to 3. Okay. Now, so for each value, 1, 2, 3, you're going to map to a unique value element in domain, which is in B, right? Now that way I define a function. Okay. So I map here. So these 3 dot basically defines a function. Now I can define another function called g. So for g, I map 1 to 3, but I map 2 to 3, and I map 3 to 4. Okay, that's g. Now let's actually use another color to represent a g. So to see what's the difference between the function f and the function g. So I can use the, let's see, a blue color. Okay, so that's g. So 1 to 3, okay, 2 to 3, and 3 to 4. Okay, so that basically defines the function g, and this defines the function f. Okay. Now let's discuss another example. Okay, in the previous example, we pick A as a finite set and B as a finite set. So sometimes this is called a discrete, set. So it only contains a finite number of elements. Now let's take a look at the example of 2 sets which contains infinite number of elements. Suppose I pick a x defined as the set of all real numbers, and y is the set of all real numbers. Okay, so x and y are basically the same set, and sometimes we use in math R, capital R, to represent a set of all real numbers. Okay, if I use the curly bracket, represent this. Now the Cartesian product of x and y can be defined as 2-dimensional space, right? So suppose x is a space represent the horizontal line, and y is the vertical one. Now every point on the x-axis represent an element in x, because x represents all the real number. For example, if I say 1 actually is an element of x, right? And this also 1 it's an element of y because it's in y-axis. Okay, now every point in the 2-dimensional space represent the element in the Cartesian product of x and y. For example, if I have particular value, say this is 1, 2, 3, 4, 5, 6, okay, and the 7. So this is actually 6.5. And then I can pick another value 1, 2, 3, 4, 5, 6, 7, 8, 9. So if I pick a value 6 and 9, then 6.5 and 9, that's an element in the Cartesian of x and y, right? So I use an ordered pair to represent a point in the Cartesian product. Now, let's define a function. So we can define a function as f. So now, for each value of x, each value x in f, okay, let's say I use f of x. So for each value x, okay, I will define the corresponding value in y as x squared. Okay, that defines a function. So this is an ordered pair. So you're basically going to say, okay, so the function can be defined as, you know, an ordered pair x and f of x. Okay, or you can define the function as x and the x squared, because f of x is x squared, right? So for each value of x in x, there's a corresponding value x squared in y. So that defines a function. Now, I can also draw a diagram on the two-dimensional space. So let's say I pick some values. I pick some values in x and find the corresponding value in y, right? So let's actually switch to a different color so I can draw this, you know, the function. So let's say we can pick a value x and f of x, which is x squared. So if I pick a value x equals 0, now what is f of x? 0 squared is 0, right? If I pick a 1, then it's 1. I pick a 2, then it's 2 squared, which is 4. And I can pick a 3, which is 9. And if I pick a 2.5, I don't know what is the corresponding value. It's somewhere between 4 and 5, right? But it doesn't matter. I just randomly pick some number. Minus 1. So minus 1 square, which is 1. Minus 2 square, which is 4, right? So minus 3, it's also going to be 9. So then we can find the ordered pair. Minus 3 versus 9, related to 9. Minus 2 related to 4. Minus 1 related to 1. 0 related to 0, 1 to 1, 2 to 4, and a 3 to 9. So let's see, 0 to 0, 1 to 1. So if I have 1, pick a 1, the y is 1, and 2 to 4, 1, 2, 3, 4, and 3 to 9, 5, 6, 7, 8, 9. Okay. 3 to 9. And also for negative value, negative 1, negative 2, negative 3, this negative 1 is 1, negative 2 is 4, negative 3 is 9. So we find some of the point. We can connect these points. Okay. Now, that's the diagram for the function f of x equals x squared. Or sometimes we say for each value of x, that's a corresponding value y. So y equals f of x. Now let's see, what is the, the corresponding value in y for 2.5? We don't know that yet, right? we can use calculator, but I also can guess the value because here's a 1, 2, 3. Now it's a 2.5. Now we can basically estimate the value here. It's approximately 2.5. It's approximately 7 point something, right? I don't know. Let's say 7. It's not 7, but it's close to 7. So that's the corresponding ordered pair. So this is actually a function which is defined as a subset in the Cartesian product of x and y. Okay. Now in the previous slides, we defined some kind of relations between two sets, right? Now, one of the special relationship is called a function. For example, if we have two sets A, remember that's the example we used, B, which contains two elements, right? So we define a function which contains the ordered pair. Now, in this ordered pair, for each value, each element in A, you can find a unique value in B. Each value in A, like a second value, 2, you can find a unique value in B, so which maps to 4, and the value 3 maps to 3. Okay, so that means for each value in A, we define a unique value in B. Now that basically defines something called a function. Now function is basically a subset of the Cartesian product of A and B, right? Now this relationship is not one-to-one relationship. Okay. Now what is one-to-one relationship, or we call it one-to-one correspondence? Now the one-to-one correspondence between sets A and B can be viewed as a pairing of each object in A with one and only one object in B. Okay, so here the first, the element 1 pair with the element 3 in B, right? But is that 3 the one and only one object in B? The answer is no, because we have another element in A, which is 3, also pairs with 3. Okay, so we have two elements in A, 1 and 3, both pair with 3. So that's not one-to-one correspondence. Okay, because on the other hand, one-to-one correspondence says, with the dual property that each object in B has been thereby paired with one and only one object in A. Okay, but now we find out for each object in B, this is not the case, because for example, object in B 3, that's the object in B. It pairs with 1, in the meantime it pairs with 3. So that F is not one-to-one, right? Now let's take a look at another example. So suppose we have A is a set of 3 elements, X, Z, and W. And B is a set of 4, 3, and 9, and also 3 elements. Okay, now if we define a relationship like X maps to 4, and the Z map to 3, and the W map to 9. Now that mapping is one-to-one, right? So X maps to 4, which is unique. Z maps to 3 is unique. W maps to 9 is unique. Because we can do the opposite. Let's say 4 maps to X, that's unique. 3 maps to Z, and the 9 maps to W. Okay, so that mapping is 1 to 1. Okay, now another example is, for example, X maps to 4, and Z maps to 9, and W maps to 3. That's also 1 to 1, right? However, if I pick an example like X maps to 4, and Z maps to 3, and the W maps to 4 as well. Now that map is not 1 to 1 because X maps to 4 and the W maps to 4. So that means, if we try to map from B to A, so then you can find out one of the element B, 4, maps to both X and the W. So that's not unique. So that's not a 1 to 1. So here we define the relationship called 1 to 1 correspondence. So now, if you look at the examples in the previous slides, you will probably find out some kind of pattern. So suppose that I have a set, a finite set, let's say A. A is A, B, and C. Okay. And then A contains 3 elements, right? Then I can always find a 1 to 1 correspondence with another set which contains 1 to 3. Right? That's pretty easy. I can map A to 1, B to 2, and C to 3, and then I find a correspondence, 1 to 1 correspondence. Okay. So if a set A is a finite set, and then we can always map to the set which contains the natural numbers 1, 2, 3. Now, depend on how many numbers, number of elements in the set. If you have 3 sets, you can map to the set of natural number 1, 2, 3, right? If it contains 4 elements, different elements, you can map to the element 1, 2, 3, 4, right? So now, basically, for a set 1, 2, and 3, now the number 3 is called cardinal. It's called a cardinal number, or sometimes called cardinality. So then also for every finite set, okay, which contains 3 elements, then because we can build a 1 to 1 relationship with 1 to 3, the set of 1 to 3, then we also say every actually finite set with 3 elements has a cardinality 3. Okay. So let's say I have another set B, which contains like A, B, D, F, G, H. Okay. So B contains 6 elements, and then we can map B to the set 1, 2, 3, 4, 5, 6. So we can easily build a 1 to 1 relationship, right? Now this one has a cardinality 6, so same for the set B. Okay. Now, so basically for the finite set, the number of elements defines the cardinality of these set. Now for an empty set, if we define an empty set which contains nothing, no elements, right? Now we define the cardinality of an empty set 0. So the cardinality for empty set is 0. Okay. So in general, a set A is finite and its cardinality is n if there exists a pairing of its element with the set 1, 2, 3, 4, all the way to n. If you can pair the element of this set with the element in the set 1 to n, then the cardinality of this set is n. Pretty straightforward, right? So we have seen that for a finite set, the set which contains finite number of elements, then it's pretty straightforward. So we can always, map any finite set to a set of 1, 2, 3, 4 to n. Okay. Now, if you can create a correspondence, one-to-one correspondence between the set, the finite set, to this particular set, sometimes we use the Sn. Okay. If we can build a one-to-one correspondence between your set and this set Sn, then we can say that the cardinality of your set is n, and so it's pretty straightforward. So now we're going to focus on the infinite set. So we're going to discuss the set with infinite number of elements. Now, in order to discuss this, we need to actually create some kind of notation which was initially used by a German mathematician called Georg Cantor. Okay, he actually used the notation called predicate formula. So he defines the set A as, use the curly bracket and put the element x. So A contains the element such that S of A, x, is satisfied. So that means for the set A, x belongs to A if and only if S of x holds. The condition S of x holds. Now, S of x could be anything, could be some kind of English statement. For example, you can define A as all the element x such that the x is a positive integer such that the x modulo 2 is 0. Now, x modulo 2 equals 0, that means when x divided by 2, the remainder is 0. Or in another word, that means x is a positive integer such that when x divided by 2, the remainder is 0. So that means x is a multiple of 2. Or x is just an even number, right? So you can define another set, okay, which contains all the element x such that x is a positive prime number. So xx can be any descriptive statement. Okay, he used that notation called the predicate formulas. So technically, we can define any set, right? Set A could be all the real numbers. Set B could be all the people who actually live in the United States. So you can define various different sets. But from math perspective, we want to study the property of these sets. So even though the contents are different, the elements are different, but we try to define, some kind of fundamental properties. Okay, so hopefully, once we actually study one set, and then we can also get the conclusion for the other sets. Now, one of the relationship between two sets is called equivalence. Okay, so two sets, A and B, are called equivalent. Okay, two sets are equivalent. Now we use the notation A is equivalent to B. If and only if there exists a third set, there exists another set. Now the members of this third set are ordered pairs such that the first member of each pair is an element of A, and the second is the element of B. So that means we can find a third set. Let's say set C. Okay, so the C contains the ordered pair, and the first element is in A, and the second element is B. Right? It's like the Cartesian product between A and B. Okay, that's the condition 1. Now, and also 2, each member of A occurs as the first member, and each member of B occurs as a second member of exactly one pair. So that means each member in A and each member in B in a pair occurs, okay, exactly just one pair. So that means if you have like a element like 1 in A pair with X in B, and then that pair is unique. So you cannot have X pair with Y. If that's the case, then X and Y must be the same. Okay. Okay. So that's if A and B are finite and A is equivalent to B, then the third set that established that TACT provides a pairing or matching of the element A with those of B. Okay. So that's called the equivalence. Now let's discuss the equivalent sets in more details. Now first look at the finite set. If A is a finite set, B is a finite set, if A is equivalent to B, so that means both A and B has the same cardinality, or both A and B have the same number of elements, right? Now, for infinite sets, now things are a little bit tricky and also very interesting. Let's see. Suppose I have a set called Sn, which is actually the natural numbers. 1, 2, 3, 4, 5, dot, dot, dot. I can just continue. Okay. So we can define these as n such that the n is an integer, a positive integer. Okay. Now let's define another set. Okay. So then we call the E of n. So it's a E of n is 2, 4, 6, 8, 10, da da da. So if we try to summarize, it's actually a set of positive even numbers. Now, if I use the Cantor, predicate formula, I can write this as 2 times n. Well, n is a positive integer, right? So it's a positive, it's an even number, positive even number. So n it could be 1, could be 2. So you can represent 2, 4, 6, 8, right? Depend on the value of n. Now we can build a third set which contains n and the 2 times n, which we can pair n and the 2n. Okay, so well, n is a positive integer. So then, for each value in Sn, we can find a corresponding value in En. So then we can build that mapping, right? So we can establish the equivalence of Sn and En. So Sn and En are equivalent. Now in here we use A and B, but I use Sn and En. Okay, it's the same. Now this is kind of strange, right? Sometimes when people ask, the question like, even though Sn has infinite number of elements, En has infinite number of elements. Now people sometimes ask, do Sn and En have the same number of elements? That question looks like it's kind of stupid because, it's an infinite set. How can we say the number of elements? They're infinite, right? But if sometimes when we build the equivalence, then you can say Sn. So if two sets are equivalent, then you can say two sets has pretty much the same number of elements. That sounds reasonable, right? However, if you look at the details, and you're going to find out En is actually a subset of Sn, right? En is a subset of Sn because Sn contains all the positive integer, but En only contains the even positive integer, or positive even integer, right? So now, Sn include the En. Also, Sn include all the positive odd numbers, right? Odd integers. So En is subset of Sn. Also, En is also called a proper subset of Sn. So that means every element in En is an element of Sn, but not the opposite. So there is an element in Sn, but not in En. For example, number 3 is in Sn, but number 3 is not in En. So it's called a proper subset. So that means En is completely included in Sn. Okay. So in this case, we call a subset of A, and also it's called the proper subset, okay, of A. But if both sets are infinite sets, then you can find two equivalent sets, and one is a proper subset of the other. Okay, but that's not true for the finite sets. We will see this in next slide. Okay. Now, for finite set, a finite set is non-equivalent to each of its proper subsets. For example, suppose I have a finite set A. In this case, A contains 3, 1, 0, 4, and 2. Okay. Now, then B is 0, 1, 2, right? And C is 0, 1, 2, 3, 4. Now we can say A and C are equivalent, right? You can build a map, right? So another one, so you can map 3 to 0, 1 to 1, 0 to 2, 4 to 3, 2 to 4. You can build this one-to-one correspondence. So you can pretty much map A and a C. But you cannot build that relationship because 4 and a 2 has nothing to map. You cannot map 4 to 1 because this can actually, force 2 elements in A maps to 1 element in B. So you cannot build that case. Now clearly, B is a proper subset of A, right? B is actually subset of A because all the elements in B also contained in A. And also there's some element in A which is not in B, like a 3. So B is a proper subset of A. But B is not equivalent to A. Now you can see that the cardinality for A is 5, but cardinality for B is 3. So A and C can build a map. So for finite set, if one set contains a smaller number of elements than the other one, then these two sets cannot be equivalent. So they have to contain the same number of elements. Okay. Now this is not true, however, for infinity sets, as illustrated with the set A and B in the early example, or in our example I use Sn or En, right? But En is proper subset of Sn. Okay, I think it's a good time to stop now because we are actually touching one of the most difficult area in math. It's called mathematical analysis. Okay, so this is a very tough area, but if we continue, we're going to be, touching the very difficult area in math. So I think I'm going to stop right here. So that's probably a good time to stop. Okay, thank you.